Hello, everyone. Thank you for being here, and thank you to the jury and the organization team for this award ceremony. So I will be presenting along with Victor the project we worked on for the past year, the E4C challenge. The aim of the challenge, as Yves Bréchet said, was to imagine a solution to decarbonize cities and try to apply through a feasibility study this solution to metropole. We chose to tackle the reuse of wastewater energy in the city of Paris. We chose Paris because it seemed an easier case study to make because we were together, the data was easier. So to talk a little bit of the context and why we decided to tackle this subject, the first thing we realized was that water heating was a major cause of energy use. So as you can see, 40% of primary energy consumption goes into the building use in the US and in the EU. And 30% of that energy goes into water heating. The second thing we realized was that water heating energy was very carbon intensive. So as you can see, in the US and in the EU, there is kind of a lot of gas, a little bit of oil fuel, and you have electricity. So depending on the country you are, electricity is more or less carbon intensive, but here there is something that needs to be done about it. And finally, most of the heat in the wastewater was just wasted because throughout the journey they have plants. Well, we lost a lot of heat. So according to the US Department of Energy, 400 billion kilowatt hour of hot water goes down the drain annually in the US. So we realized that wastewater was a new renewable source of energy. And so our main idea was to understand how we could recover this energy and how we could apply it to the city of Paris. Victor, your microphone is not on.
It's okay. So now I'm gonna present to you the approach we used for this project. So the first step was to properly define the scope of our study. This includes two main elements. The first one is the technologies. So by technologies, we mean the machines that can recover thermal energy from wastewater. The second element is the segments. So by segments, we mean the group of infrastructure where the technologies could be implemented. So by this step, we had to characterize, quantify, and size all of these infrastructure. Once we did this, we compared the segment potential in terms of energy, carbon, and economics indicators of each segment. This step helped us to conceive an action plan with a roadmap and the different steps that needed to implement these technologies in the city of Paris. And then finally, we assessed the impacts in terms of, again, carbon and energy and economics of the global action plan.
So in terms of wastewater, we identified three different types of, three different sources of energy: mechanical, thermal, and biomass. So the first two that we will focus on, so thermal and mechanical, involve physical processes that can be valorized physically. So that's the one we chose to explore. The last one is mainly based on chemical processes and is already valorized in a more central way. So mostly in the sewage treatment plant outside of the city. So as it is outside of the city, we considered that it was out of the scope of the study. So concerning the different types of water that exist, so here you can see 5 of them. As the subject is again limited to the city, we have excluded industrial and agricultural waters. We know that they have a great potential, but for example, industrial waters already been explored in different plants where they were used. So finally, we decided to work on gray waters and black waters. And the interest of domestic waters lies essentially in its proximity to the need and to the heat takers. and they also come under the responsibility of actors closer to the individual, with the possibility of smaller projects on the scale of neighborhoods or dwellings. And the runoff water have a very low potential, so we did not dwell on that. After examining the different types of energy, Victor, can you change it? We analyzed the different location where we could take the heat from the wastewater. So here we are listing 4 different locations. So we have at the bottom of the building, so at the bottom of the flat for a household, for example, in the streets. So in the street is more the sewers or the collectors. And we have also at the lifting stations. The lifting stations are places where the level of the water is raised if the sewage is too low. And finally, we have the water treatment plant. So we listed the advantages and issue for each of those locations. Water treatment was a little bit far away, and a lot of heat was lost during the way, so we didn't consider that one. Lifting station is, well, the technologies for that are not very yet well explored, so we decided to stay on bottom of the building and the collectors.
So before I present the 3 technologies we chose, there are 2 concepts we wanted to clear. The first one is the concept of heat exchangers, which is an interface that allows thermal transfer between 2 fluids. And the second concept is the concept of heat pump, which is a system that transfers thermal energy from a cold source to a hot source. So these are the 3 technologies we focused on. Biofluid, Degré Bleu, and Énergie d'eau. The difference between the 3 technologies is their position in the sewage system. So Biofluid is at the bottom of collective buildings with consequently quite pretty hot water, while Énergie d'eau and Degré Bleu are both positioned at downstream in the sewage system. The difference between Énergie d'eau and Degré Bleu is that Énergie d'eau is in total or partial diversion to the exchanger, while Degré Bleu is located directly in a series in the sewer. So we studied these 3 technologies and all their technical specificities to then link them to each segment.
So talking about segments, that's where we began to start the feasibility study for the city of Paris. So here we thought that the best way to lead this project was to separate Paris into segments of sanitary hot water. So as you can see here, we have the different segments we chose. We separated them into public and private segments because we thought that they had different acceptance rates from the actors, meaning that the public actors were more ready to accept new technologies or changes into the building, whereas private actors were more reluctant to pay more to change their heating system. So as you can, afterwards, for each of those segments, we had to calculate the volume of water that could be used for our system, and we compared it, our new system that we want to implement compared to the old system, and then measure the amount of CO2 emission we could save. So here I just added a small example about public hospitals and residential. As you can see, we have a penetration rate which is very different for those 2 sectors, as I explained before. One of the hardest part of that work was to measure the volume of water because that was a lot of data mining for us throughout many information we could get from different websites or different data sources. So it might be a rough estimation, but we still managed to find something. And finally, so we had to find the type of heating which was already existing in those places. For example, public hospitals are linked to a heating network in Paris. So it's rather a good carbon emission heating, but we measured that our solution was still better than that one. And so with those measurements, we then were able to see if our solution was good in the city of Paris or not.
So based on the analysis we did on the segments and the technologies, we calculated several indicators. So here in the green table, you have all the financial KPIs. So the capex for the implementation of the technologies in different segments for the city of Paris. As the technologies are saving energy, they're also saving money, and that's why there are profits. And considering the fact that there are profits, we can also calculate the payback. What is positive here is that the payback is quite consistent with the lifespan of the technologies, except for the residential segments. So it means that for this segment, for this specific segment, there is clearly a need for subsidies to make this technology profitable. On the bottom left, you have the carbon indicators, and so the projected impact in terms of saved carbon for our action plan. What we see here is that we could reach about 1/10 of the emissions of the city of Paris. So this is quite a positive result. Of course, it is a rough estimation. It's an order of magnitude, but what we see is that it remains quite significant. On the bottom right, you have the energy indicators. What needs to be reminded here is that we could save an amount of energy equivalent to about thousands of French households. Finally, what we want to really insist on is that we're conscious that this project has several limits. Of course, the results should be strengthened by the work of experts such as engineering firms. However, we quite remain convinced that there is a significant interest for the implementation of such technologies. The second point on which we want to insist is that there is clearly a need for a complete cooperation of all stakeholders. By stakeholders, we mean customers, engineering firms, local authorities, constructors. There's really a need for them to cooperate so that the action plan would be really efficient. This also means that there is a need for an intermediary actor that could be like between a consultancy and consulting and engineering team that could supervise the implementation of this technology in cities. Finally, we really want to thank Gilles Bordier, who was our reference from the CEA and who played a really balanced role and helped us all along the project. We also want to thank the jury for their congratulations. And finally, we want to thank the whole organization of the E4C Challenge and especially François Willem. Thank you, everybody, and have a good night.
All right. Hello. My name is Jones Goldman. Veuillez m'excuser, je ne parle pas français. Je suis en train d'apprendre votre belle langue, mais je vais continuer en anglais. My name is Jones Goldman, and I'm accepting this award on behalf of my whole team. We focused on analyzing the feasibility of resourcing biogas utilized for electric generation at prison wastewater treatment plants for use as a fuel for Paris's bus fleet to operate it in a carbon neutral manner. Before I begin, I would like to give a huge thank you to just huge thank you to the whole team. You know, these three scholars I had the privilege of working with, Kristen Klein, Arafili Jokelis, and Edvil Bertadini, are minds of little caliber elsewhere, and it's been an absolute privilege to create this proposal with them. I'd also like to thank the panel of jurors, Aaron Mabe, Francos William, Ansar Sochier, Mr. Katan, and our advisor, Professor Sala Driaga. So yeah, let's dive right into it. We focused on the transportation sector because we all know global climate change is intensifying and that the immense repercussions of unabated climate change require all of us to step up to the plate and decarbonize our cities. We focused on the transportation sector because transportation acts as a carbon lifestyle intensity leverage point, and that changes to a city's transportation can create reductions in other sectors. For instance, improving public transit can create public transit hubs and encourage housing density around those areas, reducing the emissions from residential single-family sprawl. In addition, it's not only how the transportation sector can leverage the emissions of other sectors that is of concern. Transportation itself produces significant emissions, with transportation as a whole compromising 20% of global energy demand. Transportation is truly a key pivot point, both directly and indirectly in the fight against climate change. And in the case of France, while emissions have declined significantly over the past 25 years, reducing 16.4% from 1990 to 2015, this downward trend in the transportation sector has since stagnated from 2015. And in the Eurozone as a whole, according to the latest European estimates, emissions have actually increased on average by 1.8% since 2018. French energy consumption is still on track to maintain stagnant emissions in the coming decades. So vast changes are going to need to be made in French cities if the country is going to bring its energy system in line with a zero carbon limit, especially in the largest energy consumer of all, transportation. But there is some good news. Paris is leading the way in this change, and its transportation authority, the E4C, has released a plan to meet all the city's bus requirements from zero carbon sources by 2025. In order to do this, the E4C plans to bring online 4,500 buses, 2/3 of which will be battery electric, and 1/3 of which will be sourced from biomethane harvested in a carbon neutral manner. However, you may be asking the question, why not just go fully electric? Well, there are benefits and drawbacks to both electric bus and compressed natural gas technology. Currently employed electric bus technology has a range of between 289 and 410 kilometers, whereas biogas fuel buses have a range equivalent to most internal combustion engines at around 821 kilometers. Electric buses also take between 48 and 97 minutes to recharge, depending on battery range, while to totally refuel a compressed natural gas bus, depending on tank size, takes around. Factors in a fully battery electric bus would require a greater total number of buses to operate the same kilometerage of bus routes. Biogas fueled buses can travel further and take less time to fill up than current electric bus models. More idle bus time requires more buses to run the same number of miles in a given day. Meanwhile, adopting a methane-powered bus system not only provides for greater flexibility due to the charging limits of electric vehicles, but also would save on the number of infrastructure itself, the number of coaches, the number of required service infrastructure, the number of bus drivers, and other labor costs involved in service employees compared to a totally electric bus system. And also, looking at biogas fueled buses compared to the traditional diesel buses that they're phasing out, we found that biogas buses produce 340 fewer kilograms of CO2 per kilometer travel compared to the traditional diesel buses. However, this does raise the question, though, is it a feasible technology in getting to a zero carbon level if battery electric buses can be powered by low carbon or zero carbon electricity? Well, there are a couple ways we could power biogas from zero carbon sources. One thing that's been looked at is biofuels. While Paris has committed to sourcing the fuel for its compressed natural gas bus fleet from carbon neutral biofuels, it has of yet not provided any details as to where these fuels will be sourced from. And this presents a slight issue, as not all biofuels are less emissions intensive than the fossil fuels they are intended to replace. For instance, biofuels' worst offender, palm oil, due to the land use change involved in the destruction of carbon sequestering rainforests to make way for fuel crop plantations, creates a carbon debt from land use change that is estimated to take 420 years for the fuel generated annually from a hectare of palm oil to be less carbon intensive than traditional fossil fuel usage. Rapeseed, another crop that has been touted as a source to provide carbon neutral biofuel, also has a higher emissions footprint than the fossil fuels it intends to replace and result in land use change in meeting the fuel needs. The RITP then might look to anaerobic digestion of food to meet their bus fuel needs. However, reliance on crop waste also comes with the risk in that should there be insufficient organic waste, the RITP might have to source crops further up the value chain to get their necessary fuel requirements, potentially displacing agricultural areas and requiring new land to be moved to agricultural use in order to meet the heightened and competing demands for both food and fuel. So if crop-based biofuels are not the answer to help Paris achieve carbon neutrality in the transportation sector, what is? There is a biological energy source that runs zero risk of creating land use change emissions from displacing crossland, and while you may not want to think about it, it's right underneath your feet. Waste to energy is quite simply taking a waste product at the bottom of the value chain and converting it into an energy product. Currently, 2.5 million cubic meters of wastewater run through Paris every day. Our proposal focuses on how this sewage generated by the municipality can be converted into bus fuel. In order to create fuel from waste, the following chemical process will be used. However, currently, Paris's wastewater treatment plant infrastructure collects a biogas composed of 50 to 70% methane and 30 to 50% carbon dioxide. Meaning to be used as a carbon neutral bus fuel, it would have to be further refined into a more pure methane. Currently, Paris collects 528 gigawatt hours annually of biogas from its two largest wastewater treatment plants, the Saint-Avold and the Saint-Amant facilities. 81% of the city's harvested biogas, or 456 gigawatt hours, is collected from the Saint-Avold plant. Of this, 60% is used to meet the thermal demands of the plant required by the sewage treatment process. Heating the sewage, boiling water, while the remaining 40% of the biogas harvested is used to meet internal electrical requirements of Paris's wastewater treatment plant infrastructure. If the city is to achieve carbon neutrality, biogas currently utilized to meet the thermal demands of the city's wastewater treatment plant infrastructure should be continued to be used for thermal purposes. Otherwise, some form of fossil fuel will likely need to be shipped in and combusted to make up for the shortfall in thermal energy and to provide the necessary heating energy. However, this still leaves 40% of biogas currently harvested from the city and used to meet the electrical demands of Paris's wastewater treatment plants that could instead be converted into biomethane and used to fuel the city's compressed natural gas bus fleet. Given the abundance of low-carbon electricity from France's nuclear output and the energy density of biogas compared to electricity, it would make more sense to utilize any available biogas resources towards meeting the needs of Paris's transportation sector, where France lacks a lot of low-carbon options, instead of directing it towards meeting stationary electrical energy demands like that of the city's wastewater treatment plants, for which France has low-carbon electrical energy in abundance. So, what is the potential of this 211.2 gigawatt hours of biogas currently harvested within the city of Paris to meet the city's transportation needs? How far and how much the bus fleet can we run off of currently collected biogas resources? Above is a snapshot from a GIS model of the total kilometers of the Parisian bus fleet must travel in a day. We use this to estimate the energy requirements of the Parisian bus fleet itself and how much of the currently collected biogas resources could be used, how much the kilometers the bus fleet travels could be operated off available biogas resources. We found if rerouted and refined from biogas into biomethane, the biogas that Paris currently uses to supplement the electrical energy demands of its wastewater treatment plant infrastructure could operate 89% of the total kilometers the city's buses travel in a given day. The greater range and reduced time to refuel compressed natural gas vehicles compares to battery electric buses means that each compressed natural gas vehicle would likely be expected to travel a greater percentage of the Parisian bus routes than their electric vehicle counterparts. However, biogas that's currently harvested within the city is more than enough to meet this energy demand of Paris's compressed natural gas bus fleet. The biogas capacity of Paris currently used for electrical demand could be rerouted without impacting the thermal requirements of wastewater infrastructure, and as I said, would provide more than enough to operate its local transportation needs. Creating an energy solution that is both zero carbon, local, and resilient. And the Paris Public Transportation Agency is already building the infrastructure to handle methane for its bus fleet, having placed an order for 1,500 buses compatible with methane. The demand for methane will be there by 2025. The question is simply how city decision makers will meet this energy demand. And this is why our proposal is so important. As while the Paris municipality has stated its intention to operate its compressed natural gas bus fleet solely from carbon neutral biomethane, it has not yet released a plan as to where these resources will come from. And while there is no current sourcing plan for carbon neutral biomethane, what there is in France is an established fossil fuel energy import system for natural gas, as the country imports 60% of its liquid natural gas fuel from nearby Algeria. Without a readily available alternative, it would be easy to fall back on relying on Algerian energy exports due to the existing established energy pathway of convenience. It would be immensely tempting for decision makers to delay the full implementation of carbon neutrality within Paris's bus system and fall into existing, though far from carbon neutral energy pathways, utilizing fossil fuel gas to meet the city's bus energy needs, especially as Parisian bus authorities in the E4C intend to fuel a portion of their compressed natural gas bus fleet with natural gas imports until 2025 or until they can completely find suitable replacement. In conclusion, we believe that by looking at Paris and other cities as an integrated energy system, a more strategic optimization of energy resources can be made within the system as a whole, rather than what is currently made by decision makers within the information silos of their own organizations. It makes sense for the managers of a city wastewater infrastructure, given the realm that they oversee, to utilize biogas for electrical energy needs of the plants they operate. However, when the needs in terms of energy mobility and the limitations of existing battery electric bus technology are considered, energy use can be optimized by utilizing available biogas for use in transportation and sourcing the resulting electrical energy requirements of wastewater treated infrastructure from the grid for stationary electrical needs. So we can actually meet both transportation and wastewater treatment plant infrastructure and electrical energy needs in a carbon neutral fashion and meet our goals under the accords that bear the city's great name. Thank you very much.